You're amazing. Really quickly. Almost everyone's here. Really quickly, Mr. Park. Remember you guys got those green sheets the other day?
Yeah.
You had to do some tutoring hours before the end of the semester. Mr. Park would love someone or someones to be available like a certain afternoon to come in, just chill in his classroom and be able to work with kids in geometry, algebra 1A, etc. Now, I love it. So I've only told your class. Calculus they should be helping calculus kids, or you guys, they're busy. But you guys, just go talk to Mr. Park, he'll give you a day.
There we
Or
go.
he'll give you a time. All you gotta do is sit and be available. And the nice thing is, he would like it in his room, and if you want tutoring like volunteer hours, you could talk to Senor Brache. I'm sure he might be able to work with you in the sense of like, hey, I'm doing it for Mr. Park, he would love us to work in his room. Like if you're worried about the volunteer stuff for college, etc. I would talk to Senor Brache and be like, hey, can I do your tutoring but in Mr. Park's room? Because Mr. Park would love for you to be in there. That way if you have a question, you can go to him about it. And that way also he can see which kids are getting help, etc. It just helps him out. So anyway, just pop into his room at some point today and be like, hey, Miss Dueck said, and he's like, oh, sweet. And he'll be so excited, and then he won't say it. But either way, he'll be excited. He'll probably set you up with a day, maybe once a week. And you'll have that thing like busted out as quickly as you would say 1, 2, 3. Sound good? So many people raise your hands. Go talk to him today. He would love to see you, talk to you, and put you on a certain time. Cool? All right, kiddos, let's go ahead and get back on to notes. We are talking about, wait, what's this stuff up here? What was yesterday? Calzones! AKA, we are talking about measuring angles in radians, right? I know, you didn't have nutrition first. I'll stop talking about calzones for at least a little bit. But we were talking about radians. And on this page, how was I trying to get you to think about radians? Strict memorization, do you think, or understanding? Understanding. Understanding what an entire circle has as an angle measure in radians, which would be 2 pi, right? Half a circle would be a single pi. Whole circle would be 2 pi. There's a gal on the internet who's like, we should boycott pi because it's lame. It's only half a circle. We should go for tau, which is 2 pi. She says we should celebrate Tau Day, but it's during summer, so if you want to celebrate a day during summer, when you can do it during the school year, you get free pie. But anyway, pi is what it is. It's a half circle, right? And we were talking about fractional pieces, true? And I was just giving you certain random radians that weren't even written up of the ones that you guys initially did. And I was like, hey, can we understand where 3/4 of your calzone would be, right? Or where 4 pi over 3, 4/3 of your calzone would be. Oh, hey, it's a whole one, and that's a little bit more. Or where 11 pi over 6, 11/6 of your pi or of your calzone would be. 1 5/6. Oh, hey, it's almost 2, just missing a little 6, right? If we understand the fractions, life will be a whole lot easier. But then we said, well, there is technically a mathematical way to do it with building bridges. There technically is a mathematical way of doing it with building bridges. We'll talk a little bit more about this today, but I figured that why not, let's just finish what we were starting at the end of yesterday. We got that the pi's canceled. Technically, pi does not mean radians. Pi is a special number in radians. You guys noticed when I was doing that whole arc length over radius formula, the units canceled out, the centimeters went away. Radians are technically dimensionless. There really isn't a unit, but we still say radians just so you understand that's what we're measuring in. Radians are a measurement based on the radius, whatever unit it has, centimeters, inches, miles. Kilometers doesn't matter. So the pi does cancel because there's one up top and one down bottom, but what we're technically canceling is the units. That's why we built the bridge the way we did with 180 degrees on top, and pi is how many radiuses wrapped around the circle. Remember, radians? How do we finish this off to figure out how many degrees 3 pi over 4 is? Multiply 5,040 all over 4. Now we can divide. 4 into 5 is 1. There's a 1 left over. 4 into 14 is 3. There's a 2 left over. 4 into 20 is 5. Hey, that's 90 plus 45. That's a 45-degree angle in the second quadrant. Number next one. The radians cancel. Okay, cool. Left with degrees, cool. Pi's cancel. Is there a faster way than multiplying 4 times, like the top number times the top number every time? Yeah, how many times is 3 going to 180? So anytime you have an over 3, guess what? Guess what angle it's going to go to? 60 degrees. Anytime you have a 4 in the bottom, it's always going to go to, we could have reduced this puppy and we would have gone ahead and had 45. Fourths are going to go to 45s, thirds are going to go to 60s, and sixths are going to go to, you guys see it? 30s. But how many 45s? 3 of them. 45, 45, 45. 4 of them. 60, 60, 60, 60. Let's see if that works out. 4 times 60 is 240. 135, he's over there, 3/4 of a calzone. 240, that's 180 plus 60. So that's 1 and a 2 and a 3 and a 4. Or 1 1/3 of a calzone. And 11 times 30 is 330, which is going to end up being almost 360, just 30. Which ends up being our almost 2 calzones, 1 1/3 calzone, and almost a whole calzone. Why am I saying calzones? I don't know, because some of you guys have memorized this unit circle and you could not get even like above an F on a quiz if I was to give it to you right now. Struggle. Maybe you had it really well last year, but it doesn't mean you have it now. Trying to make sure, at least as far as angles are concerned, you have an understanding about how to know where the different radian angles are. We'll come back to this in just a little bit. Let's keep going. We need to talk about a few special types of angles, and one of them is called coterminal. Come on, my English nerds. Co. It's a prefix. That means what? With or together. True? True. Terminal. Think about that little graph that you wrote at the very beginning of section 4.1 yesterday. Terminal side. The terminal side is the side at which the angle does what? Terminates or ends. Look at us using English to help us with math. Go team. So co, with or together. Terminal or ending side. Angles that end at the same place. Angles with the same angles with the same terminal side. Angles that share a terminal side. Man, you can almost get that just from reading it. Right? Co-terminal, ending at the same place, sharing the same terminal side. Measures usually differing by a multiple of. Yeah, good idea. Let's talk about why first before we fill it in. Someone give me in degrees an angle. 60 degrees. First one I heard. About there, right? How can I think 60 degrees? What's an angle all of you know? Corner of a paper. 90. 60 is what portion of 90? 2/3. Oh, just think about cutting it in thirds and then go 2 of them, right? Hey, what would 1/3 be? Oh, nice. What would 1/2 of 90 be? Nice. Hey, those are the 3 important angles of my unit system. Anyway, coming back. So I have 60, right? You can go from 0 to 60 in degrees in a rotation. And you end at this spot, right? You end at that terminal side. But what's another way of ending right there with a different angle measure? If you go and you spin once and then you end. Aren't you going to be facing the exact same direction as the guy who only spun a little bit? If you want to be super snazzy, couldn't you even spin backwards and end facing the exact same direction as the guys who went a little bit or went a whole lot more? Uh-oh. How many different co-terminal angles are there? Infinitely many, because you don't just have to spin once. What else could you do? Couldn't you spin twice? Couldn't you spin 3 times, 4 times, 5 times?
Yes.
So instead of saying all the different possible, we'll say it's a multiple of. A multiple of what? Well, if going in the positive direction, going up 60, how do we get back to it? We go around another what? 360. We're going all the way around the circle. So multiples of 360 degrees. Or remember, we're trying to get better at radians. Or how many radians? 2 pi. True. Remember, they're equivalent, but measured differently. By a multiple of 360 or 2 pi. How would this be different? For instance, I said we can get there by turning 60, right? We got that one done. But question. Do you remember the second one I did? What was the next one I did? What would that angle measure be? 420. How come? Because it's 360. Sorry. You could think it's 60, right? Plus a whole 360. Or it's 360 plus a 60. Either way. 420. No jokes. What was another way of getting there? Backwards. We'll get there in a second. Sorry, I got distracted. I started going on this one. What would that one be? 780. How? Add another 360, right? So multiples of 360. Add 1 360, add 2 360s, add 3 360s, right? You keep on adding 360 all day. Or you could, how do you go the other way? You could start at 60, right? And then how do you get back going the other direction? Subtract 360. So 60 minus 360, that would be negative 300, right? What would be another one without me even drawing it? Yeah, we could subtract again, and that'd be negative minus 360. Oh, that's fun. Someone pull that. All right, kiddos. All right, kiddos. So, with all the work that we did outside, I'm thinking if you're still out wandering the campus somewhere, you can listen to it later. There is a general formula that we can go ahead and state that can be called the definition of coterminal angles. Okay? Now, hold on. Why am I using a funny Greek letter?
Because we need to.
To distinguish it from another funny Greek letter. This one's theta, and I just use a different, right? Just to distinguish it and say, hey, it's a new angle. But they're related, and how are they related? They're related because if two angles are coterminal, that means the second one needs to be the first one plus some multiple of 360, and we show multiples by writing an n after the 360. Now here's who n is. N is all possible integers. Wait, who are integers again? Numbers. What kinds of numbers? Negative 3, negative 2, negative 1, 0, 1, 2, 3, right? Positives and or negatives including 0. No decimals, no fractions. I can't have decimals or fractions of 360. It needs to be a whole 360 away, positively adding or negatively subtracting. I can keep on adding or I can keep on subtracting. That's all well and good if you're in degrees. How would this change if you're in radians? Exactly. So the n is the same, showing different multiples, adding 2 pi, adding another 2 pi, subtracting 2 pi, subtracting another 2 pi. And as we saw outside, it might be easier to make those into the fractional pieces of the radian that you're dealing with, right? But technically, coterminal angles, yes, they end at the exact same side, but what does it take for them to end at the exact same side? Being 360 away in degrees or 2 pi away in radians. Does that make sense? Okay. A couple more seconds. Yes, you guys did a great job outside, thank you. Not all classes could handle that. Definitely not all classes could handle that. But that's why you're honors, right? Yes. Responsible, on top of things. Never procrastinate.
Ever.
Yeah, sorry about that last one.
Maybe we can do that.
We all have our moments. We all have
But you work hard when you do procrastinate because you don't want to fall behind.
That's right.
Yeah.
Is that better?
Yeah.
And let's say it's not procrastination, let's say it's time management. Okay.
There we go.
Prioritizing.
Right.
But hopefully we become wiser and wiser in our priorities and in our decisions.
Okay, I think I'm showing.
Good?
Gucci.
Uh-oh! Man, bummer. I wish we didn't have a fire drill. Because then we could have learned what these two are. Just kidding. They are. What's it take for two angles to be complementary? Add up to 90. No negatives though. No negatives. So it's only possible. I do a little angle abbreviation for angles less than 90. And it's only possible for two angles to be supplementary as long as they're less than. My less than became one word. I don't think that's grammatically correct. Okay. Complementary. Two angles that add to or sum to 90 degree. Yeah. I don't know why I got confused for a second. But, we're trying to get good at radians. 90 degrees or who or what? Pi over 2, half a calzone, right? For supplementary, we're going to add 2. From geometry, you'd say 180 degrees, but now that we're doing radians, or 1 pi. Calzone, out of home. Calzones are better.
The more we say calzone, the more like my mouth starts to water. I'm so hungry.
This is true. But are we thinking of a semicircle? Are we at least like visualizing the right food?
Yeah.
Okay,
Yeah.
Work on this.
You gotta after building calzone, seriously.
Now we know. Question. Question. What would be the complement? What would be the supplement of pi over 5? What? That's not special. Pi over 4, pi over 3, pi over 6 are the only special ones. Doesn't mean there aren't more. We just don't deal with them a lot. But how do I find the complement and supplement of pi over 5?
I'll do an 80 divided by 5 then.
Oh, he's going to change to degrees and then back to radians,
what
which
if
we can
okay.
do.
Well, what if? Okay, so what if since we know it's pi over 2, they have to add up to pi over 2. So another angle, which we could call a different Greek letter, So if we add the two angles together, they would have to equal pi over 2. So if we subtract the theta, the pi 5. We subtract that, then we can get.
Does it make sense that if they add up to be pi over 2, you can subtract from pi over 2 and find who's left? But they have different denominators. Child's play. What's going to be our common denominator? 10. How do I get 10 from 2? Multiply by 5. How do I get 10 from 5? Multiply by 2. So what's our complement? 3 pi over 10 sound good? Yes? Right? If they add to be pi over 2, then if I subtract from pi over 2, I should figure out who's missing. And what am I going to do for supplementary? I need to figure out who's going to get me all the way to, let's do beta, to pi, right? But maybe this one's easier, because one whole calzone is how many slices of 5? You have all 5 of those 5, right? So if you have all 5 of those 5, if you're doing pi minus pi over 5 in order to get to beta, well, don't we know 5 over 5 minus 1 over 5 is how many fifths? 4. We're missing 4 of those slices. Does that make sense? Now, just in case you're like, I like Luca's idea. I like the whole go to degrees thing. Okay, technically you could. But you would have had to take pi over 5 and say, all right, pi over 5 is in radians. I need to get rid of the radians. So put a pi down there and 180 up there, and then be like, ooh, 180 over 5. Huh. 5 into 180 is going to be 3, and then carry the 3 and 0. That's going to be 36 degrees. All right, now you need to go from, right?
18 over 5. Wait.
Yeah. And now I need to make it to 90, so I'm going to do 90 minus 36, which is going to end up being, 60, 54. Ah, stink! Now what do you have to do to get to 54, to 3 pi over 10? Go back to radians. So then we have to go ahead and take that 54 degrees, and then we have to say, I need to get rid of degrees. Wait, who's going to go on bottom if I'm getting rid of degrees? The 180. And the pi is going to go up top. And then you have to say 54 over 18. That's easy to reduce. Said nobody ever. Guess what? If you divide by 3, this one ends up being 18. And if you divide by 10, that one ends up being 18 as well. You end up with 3 pi over 10, but it might have taken you a bit of mental calisthenics to get there. Could you get there? Yes. I might think, though, that common denominators are just a little bit easier, yeah? Maybe. For some of you, maybe not. But you're going to have to deal with a fraction eventually, and you could reduce that, divide by 2 again, divide by 2 again. But maybe it's easier just to keep it in radians the whole time. What if I say you pretty much know this entire page? No. Really? Yeah. Pretty much. Let's check it. Ready? Let's see if you already know this whole page. Who is a degree? Do you know by now? How much of a rotation of an entire circle? 1/360th, right? Is that very exciting? No siree, which is why, well, not degrees, sorry. Which is why it's necessary to get away from degrees and go to radians. Degrees say you better figure out the rotation, you better take a certain 360th of it. Radians say, whatever units you're in, I can tell you where to go, whether you're in inches, centimeters, miles, or anything in between. Converting. Dimensional analysis. Oh no! Oh wait, that's just building bridges, right? Dimensional analysis. That's a snazzy way even in chemistry of talking about this thing that we've been doing. It's just building a bridge. Converting by multiplying by 1 creatively. Multiplying by 1 creatively. Oh, that's right. You have to have the same or an equivalent statement top and bottom, right? So if we have some number of degrees, let's just say x degrees, just to make it mathematical. If we have a certain number of degrees, what's the conversion factor? What am I going to multiply? What's going to be on top and on bottom? Degrees on bottom. How come? Why'd you know? Because you need these little degrees to go away, right? And what's equivalent to 180 degrees? Pi.
Shoot.
Then you end up with, well, you're going to have to actually do your multiplying, but remember the x is going to get multiplied by the pi, and the 180 is going to stay below, and then you reduce if possible. And there's not really a label because radians are more understood. But what if instead of having degrees, what if you have x with no degree mark? And he's standing for an angle and you know it. Well, if there's no degree mark, he must not be a degree. He must be a radian. And if he's a radian, what am I going to multiply by? I need the degrees up top. I need the pi down bottom. Oh yeah, cancel with. Do I always cancel the pi? Depends. I can only reduce him if there's a pi in this part over here. If there's not a pi, he's going to stay, and I'm going to end up with x times 180 degrees all over pi, and I'm going to reduce it if possible, and that's my final answer. Can you have pi in a degree thing? Because pi is just a number. Pi is just a number. Represents something super special in radians, but he's just a number at the end of the day. So what canceled out? This one, the degree mark canceled out. What canceled out here if not pi? The understood radian that we never write because we don't really need to, because the absence of a degree mark shows a radian when talking about angles. Do we have it? Didn't you know most of the things on this page? Maybe not mastered it, maybe not ready to get an A on a test over it, but at least we kind of saw them, right? Good. Okay, so what if something gets weird? What if something gets weird? What just got weird? Stink. Application problems, that's a thing in this section? Kinda. Let's see if we can put it all together. Ready? Arc length. Where have we seen arc length this lesson? In a very special formula yesterday at the very beginning when we talked about radians. We saw in an earlier formula, and technically maybe we don't even need to really stress about memorizing more formulas, that theta equals S over R, where R was the radius and S was the arc length. Question. Do we really need a new formula to solve for arc length, or could we just start with the original one that we had since the beginning? Yeah, we can just use the original one and plug and chug and then move stuff around as we need to, right? So if we have this problem below where it says a circle has a radius of 4 inches, okay, R equals 4, as they show. Find the length of the arc. Find S when, find the length of the arc, find S, when intercepted by a central angle of 240 degrees. Theta equals 240 degrees? Yay, go! It's going to be wrong. No! Why is it going to be wrong? We figured out the angle is 240 degrees, that's theta, R is 4, find S. It's a simple plug and chug, except what kind of measure of angle was this formula telling us about? Radians or degrees? Radians is dependent on the distance around and the distance across. So we're not allowed to plug in degrees because remember, degrees have different numbers than radians. So I need to change it first. I need to say, uh-oh, he's in the wrong form. Just think he has the wrong unit. So what are we going to do with our 240? Times, careful, 180 on the bottom, right? Pi on top. Our degrees will cancel. We'll end up with, divide by 60, right? We're going to have 4 pi over 3. That's our theta. And now we're going to plug and chug. True? All right, cool kids. Fully attend homework by tomorrow. I realize there might be a couple application-y ones at the end that you didn't see examples of, but we'll go over them in class and make sure we're good. The applications aren't the huge point of the section. So do the best you can when you get to the application-y ones at the end. Bye, guys. You guys too. Happy nutrition. Enjoy going outside again. Are you going to be at the school?